So thank you very much, Ariane, for together and nice to see all of you here. I mean, I can see very good friends, so it's nice to have this event. And so I will be. I'm sorry if some of you have already attended this presentation. I try to change it from time to time. I mean, so this is the topic. So what I will try to do, I will try to discuss this new technology that we have been working on for a while, which is called SIM. And so in principle, I mean, this should be a kind of technology that merges together three things, which is communication, computing, and sensing. And essentially, the main idea is try to do everything in the web domain. So in one of the last presentations that I gave, there were people from China Mobile, and they asked me whether this will ever be in a generation. I'm not totally sure whether this will be I mean, definitely will not be in 6G, but whether it will be in any generation, I don't really know. But I think that it's a nice, I mean, topic, I mean, to explore with many questions. So let's see what the technology will allow us to do. So I will talk about the two main things. So for those of you who are not working on smart radios or smart radio environments, I will give a very brief overview. So first of all, I have about 40 minutes. Okay. So and this is just a recap, and then I will move to what now I call, or many people call, deep diffractive radio, deep diffractive radio. So which essentially is to have many layers of metamaterials and try to see what we can do with them. So, and I started with the radio with Guglielmo Marconi because there was a couple of weeks ago, there was in Rome an event with photonics conference of the IEEE, and they organized a nice event on the 150 year, I guess, from Marconi. And there were many people, I mean, from the foundation who were talking about him. So we discussed about this evolution between the actual radio to the smart radio environments to what it's happening. And also I will try to show you that this deep diffracting radio has been quite well developed, I mean, in the past, and assumptions within the photonics community. Okay, so very briefly, so we know what happens in a conventional radio environment. The wave propagates and they recombine at destination out of phase. So in principle, we should optimize a lot of transmitter and receiver to compensate for that, and this consumes a lot of power. Another thing is the blockages. So the signal do not penetrate the obstacles, and then we may be out of coverage. Okay, that's just a quick recap. So with the smart radio environment, what we want to do is to deploy reconfigurable surfaces where we have antenna elements and electronic circuits. So the modeling is pretty complicated, the electromagnetic modeling. So now for today, I will keep the usual model, which models each element as a phase shifter. Okay, so I'm working quite a bit on this electromagnetic modeling, but for today, I will not really be talking about that. Okay. So each element is a phase shifter, we can control the phase. And okay, so we deploy these metasurfaces, and in principle, what we can do is to make sure that all the waves reach the destination in phase, and we can get some power gain. And even better, we can actually change the direction of propagation. That's essentially what we can do. For those of you who are not working on that, the main idea behind this approach is what we call the generalized Snell law. The Snell law is very well known. Angle of incidence is equal to the angle of reflection. Here, what essentially, the reason why we control the phase, and by changing the phase on the surface and applying a field gradient, we can change the difference between the sign of the angle of incidence and the sign of the angle of reflection. That's essentially a very brief, a very short background for if you are not working on this topic. Now, the problem is a very intuitive way to explain the things. The point is that this law does not really work in practice because you can change the direction of propagation, but you don't know how much power goes in that direction. That's the main problem. So all the people who are working with metamaterials, they are trying to develop other techniques, more advanced techniques, to be able to make sure that the efficiency of the radiation is high. Okay, so that at least
this will give you a simple idea. Okay, so let's now try to see the main idea. The generalized linear law was actually initially proposed in that paper, and the reason why we people are interested in technology is because of simplicity. So no power amplifiers, no DSP, no RF chains, and so on and so forth. And we would like now to keep these properties, is what I will be talking later on. And I will try to make the connection with what is happening in optics. Okay. Okay, so the main property that we like about this technology is to do everything in the web domain. This was the first example. And then now I will try to show you something new where this concept of doing the web domain gets much more emphasized. Okay, so we don't need to do like in conventional relays the decoding, the modulation, and so on and so forth, and then go back, but we can simply basically reflect or transmit the signals throughout this device. Okay, so this was just to make sure that everybody could get the point. Now, the next step that we are working on is what we call, or what I mean, at least we call with a buzzword, this machine learning in the web domain. So what is the idea? The idea is that we know how a typical feed-forward deep neural network works. So we have one input layer, one output layer, okay? And then we have many hidden layers in between. The key point is that this device operates in the digital domain. So we take an image, we make it digital, and then we do all the processing through the layers and the neurons. Now, the idea would be, can we make the same processing, but directly in the RF domain, so in the electromagnetic, yes, should do that. Okay, so in the electromagnetic domain. So that's essentially the main idea, and the objective is to try to see whether we can use this reconfigurable metasurfaces to do that. That's essentially the main goal. So, is this idea new? So now here we start from something, I guess, more interesting. So is this idea new? So this idea is not totally new in a sense. Maybe the way that we want to implement it, there are quite many differences from what we can find in the literature. But indeed, I'm not sure whether this is the real first paper. It's one of the earliest papers that I found. We are still looking whether there is any earlier paper. But here, the authors, and among them, you can also see that there is a value which is very well known in the machine learning community. They are actually proposing to integrate into the digital processing some analog components, because the analog components are those that allows you to reduce as much as possible the power consumption. So if everything was analog, we would be able to have a huge power saving. Okay. Of course, digital processing gives us flexibility. We understand, but now the reconfigurable metasurfaces, in principle, should give us this flexibility as well. We are not at that level today, but I mean, we were much farther 5 years ago when people started working on this. Now we do have the platforms. Many companies have the platform to do something interesting. I mean, okay. Now, even so, for those of you who may be working on metamaterials, Christophe Callot wrote this paper more than 10 years ago. He's one of the main experts in reconfigurable metamaterials, the theoretical part. Was a professor in Canada, now back to Belgium. And he wrote this paper arguing that we should try to do almost all the processing in the analog domain. He was thinking about the metamaterials as a way to make everything simpler. Okay, going from digital radio back to analog, because everything was analog at the beginning. Then we moved to digital. Now it seems that we are going back to analog. That's essentially the idea. Then, I mean, the paper that, at least to the best of my knowledge, brought this idea of machine learning in the web domain to the big audience is this one, published in Science by Odskan. And here you will really find the concept, the way that I'm trying to propose it to you. Everything was done in the optical domain. And in this paper, you will find, okay, again, I mean, the motivation is to reduce the power consumption and to make it simple, things simple. And you will find a figure of this kind. where they really want to make it, trying to compare, to contrast what they call electronic neural network, which is what we are using today, so what we use today, against what they call diffractive optimal neural network. Diffractive, because it's not like a RIS that reflect, or most RIS reflect, but the signal goes to the layers. Okay, so that's essentially the name. And also, but there was basically this paper got a lot of attention. They also made the hardware, implemented the hardware. But I go directly, I go straight to the main point. One of the main complaints about these papers that people started discussing is that they were claiming the machine learning performance, but the system did not have any nonlinearity. And still, all these systems that are available, they have most of them, basically all of them, they have non-linearities. So even though I will show you that we do get a lot of gains by applying the multi-layers, but still we are very far from what a true machine learning technique, solution can do, because the non-linearities are unknown there. Now, the same authors recently, I was checking their papers. They have a few papers. If you go to the website of OutScan, you will find a few papers there now. They are trying to develop non-linear components to be integrated into this. And there's also Andrea Lu from City University of New York, who has developed some non-linear elements that may be integrated into this. So this seems to be a big thing. Okay. But still, we would see that we have some gains. And in fact, even though there are no linearity, people will start talking about the depth, the impact of the depth of the structure. Okay. So, but you can have a look, and if you want to read this paper, the actual paper, it's short. It's you need to go to the supplementary materials, and then and then you will find the useful information for answer. Okay, so now another main limitation. So was the first paper. So one of the assumptions was that this device was not reconfigurable, or static. Okay. Then 4 years later, there are this group, Taejun Kui. And for those of you who are working in metamaterials, this is one of the best teams that exist on the reconfigurable metamaterials. And they said, okay, nice. You guys proposed this diffractive neural network, and we added the reconfigurability. And so they developed an hardware that is actually reconfigurable. But it's very different. These are the best guys who have the hardware on this, okay? But they developed an hardware. If you can read each mid-atom of this hardware, is integrated with 2 power amplifier chips, and there was a modulation range of 35 dB. So it's a completely active device with power amplifiers, etc. So it's completely different from the concept that we have in the concept of RIS. So no power amplifiers, no DSP. Here is another story. We go back to something that is active with a lot of different. So at the end of the day, the structure was like this, which is not even something simple, but it was working. Okay. So there was the usual receiver, the transmitter, and this was the actual SIM, the actual what they call, I think they call PAIM, something like that, programmable AI machine. So, but they made some experiments like image recognition, etc., and it was working well, but still it's active. And their idea is to develop a kind of device of this kind. So you have this again. This now multiple layers of reconfigurable metamaterials, and we go back later on. And then you enclose this in a structure where the waves cannot go around; they can just propagate towards the longitudinal direction. Then we go also. Then in a while, I will also start talking about. We need to assume that the waves only go through; they cannot come back. And that's another big problem. Okay, in practice, even though there are some solutions. Okay, so now I'm not going to give you all the the historical background here, even though it's very interesting. And in any case, if you want to know this, you need that. You will not find anything in TCOM, T-Wireless, except the papers that I will show you. If you really want to see the historical background, you need to go to paper synoptics. So science, physical review, this kind of. By the way, there is a nice overview if you just are interested. No, it's a little bit small. Sorry. But in any case, I can give you the slide here. This is actually one of the latest complete overview papers where there are hundreds of references. So you can follow it. The name is Diffractive Deep Neural Networks, Theories, Optimizations, and Application, and it's published in Applied Physics Review. Okay, so I can give you the slides if you want, with the references. And what's going on? Too fast. Yeah. So if you wanna in any case have a look, there is in many of the papers you will find that many people claim that one of the advantages of this technology is that the processing is done at the speed of light, which is true. But then I mean there are experts like in this paper here where they claim that this is not the main advantage, and in this paper they list what are the 11 main advantages of doing optical computing. And then there is another expert in metamaterials, Francesco Monticone, who is a former PhD student of Andrea Lu, who try to discuss what are the benefits of metamaterials for optical computing. So I think that the community is converged. Metamaterials for wireless communications, we are trying to converge towards this kind of things. Okay, with all the assumptions and etc. that basically exist. So now, that being said, how this fits into a wireless community. So we got inspiration from these papers, and we started working on this technology, which it was called stacked intelligent metasurface, which is essentially this deep diffractive neural net done with metasurfaces, not necessarily in optics. And then we remove everything that is active. Okay, that's essentially the idea. So this was proposed at ICC in Rome. And this is actually, if you want, really the combination of evolutions in neural networks, electromagnetic computing, and reconfigurable metamaterials. And then the concept of diffractive networks, which is basically what originated there. So, and then I will try now to go briefly on 4 main items. So, I will just clarify the stacked intelligent metasurface. What are the possible advantages in wireless communications? And I will try to highlight 3 possible applications. One is to use for base stations. One is to use for simplifying the implementation of the optimal design. And then one is really to do computations in the world domain. And then I will link this with ISAC. So essentially how you can do communications and sensing together. Okay, so at the end of the day now, this thing is essentially what I've already told you. So you have multiple reconfigurable metamaterials, metasurfaces, stacked, and the signal propagates from one layer to another. So it's not a reflecting surface, but it's a transmitting surfaces. Of course, you may have that the first layer is jointly reflecting and refracting, so the transmitting, where you basically have, it can be a star, what people call star, simultaneous transmitting and reflecting surfaces. So you don't lose this property of the reflection, but essentially you may have it put on a wall. You may reflect the signals in the room, but you also help the signal going through the other room. So, for example, for military people, they are trying to use this for through the wall imaging, through the wall radar. Okay. So, and the idea is now very simple. So each layer is a reconfigurable metasurface, and each neuron is one of these reconfigurable elements that you have. We still assume in all the models that exist that the system is linear, so there are no linearities at all. If you use electromagnetic models, on the other hand, non-linearities kicks in any case, but of course you cannot control them. So you are still far from the activation functions that people use for DNA. Okay, so what are 3 possible applications of these SIMs which we studied, and we showed that there are some gains. One is simplifying the base stations, the design of base stations. So the main idea of a base station, the design that we have today for a base station, is a sophisticated DSP, and then high resolution DACs, and then RF chains, and other things after. Then, I mean, here the idea would be to try to reduce as much as possible the digital signal processing. Now, if you ask companies, I think the way that is presented here will never happen. That you will not do anything in the digital domain. You may do something in the digital domain, some hybrid, but I mean, the idea is to reduce this as much as possible. Then you have a low complex, low resolution cases. And then in principle, we could fire the signals from the antennas. We have a seam just very close in the near field of the antennas, and then the signal propagates. And essentially, what you do is the pre-coding in after the signal leaves from the antennas. Everything is in the near field. Okay, and you do something similar to this. This is a short term because it may be simple to stack many antennas together and then to put them in front of the antennas. And one, I mean, much nicer implementation would be this one, where you have a real surface, you have the feeder directly integrated into the surface, and then you have okay. So this would be the ideal solution, which is a little bit more long term to be implemented. Okay, so the main motivation is the following. If you go to the papers of analog to digital converters, they will tell us that there is also a paper from Angel Lozano, 1-bit ADCs for terahertz communication, where basically the concept is that the power consumption for ADCs increases exponentially with the number of bits that you use for doing the analog to digital conversion and linearly with the bandwidth. So conceptually, in principle, if you could do that, you could reduce exponentially the power consumption. If you use 8 bits, you're going to drop by a constant to the power of 8 your power consumption, which is huge. Then what you can do in practice, it needs to be understood. But I mean, that's the scaling law that we could have. And that's the motivation. Now, another main for this device is the following. So, as I said, in the RIS community, we are mostly used to reflecting surfaces. But there are also other applications. For example, for outdoor to indoor communications, for room-to-room communications, you may plug the metasurface on the wall, and then you may try to get a better signal on the other side. And there are now experiments that have shown that this actually works. So now let's consider this example, and then let's think of what we do in general in wireless communications. The typical model that we have is the so-called diagonal design for each metasurface. So we assume that there is a decoupling, electromagnetic decoupling between the elements, which in practice, and there is a decoupling, and also we are not able to control the scattering of each of these elements jointly. We assume that we are able to control them individually. So essentially, this implies that we have a controllable impedance connected to each reconfigurable element, but there is no cross connections between the elements. Now, in practice, you have many reconfigurable elements on the surface, which are very, very closely spaced. And so there is a lot of coupling between the elements. If there is a lot of coupling between the elements, this individually controllable structure is not the optimum that you can get. Okay. Let me see if I did that. In fact, I mean, with David and all the other people, we wrote some time ago with this paper. There is also a lot of work from Bruno Clerc on this. But what we have shown is that the optimal design, if you solve the capacity, if you solve the optimization problem, the optimal design for a RIS is a design where the matrix of transmission or reflection coefficient is full, it's not diagonal. Okay? We did the proof is that you do the singular value decomposition of the first op, singular value decomposition of the second op, and then you end up having that the optimal matrix is the product of two matrices, and these two matrices are not diagonal, and you get a non-diagonal matrix. Okay? So this is essentially the best that you can get. The problem is that this best that you can get gives you circuits, a control circuitry of this kind. So you need to put a lot of controllable elements into a very tiny space. If you have a spacing lambda over 2, you need to put a lot of hardware. Now, I mean, we know that, especially if you go up in frequency, you find, for example, diodes so small, it's very, very difficult. And also, you need to put many. So we talked also with many companies. We tried to submit a European project. And when we said what is improved, when then we said, would you like to implement this kind of solutions? Not all the companies were, super happy because it's optimal, okay, it's nice, but it's very difficult to implement. On the other hand, they were a little bit more prone to implement a stacked version because it's simpler. Now, why I mean the stacked version then in this case? Because let's take let's see how this divide works. You have one layer and then you have another layer. Now, imagine that each layer has a diagonal response, so a diagonal transmission coefficient. This layer and this layer. But when the signal propagates, is scattered from one atom to all the other atoms in the second layer, this channel matrix is full. So basically, we have that the end-to-end channel is the product between the transmission coefficient of each layer, which are diagonal matrices. So we assume that they are diagonal. And then we have the connection between all these atoms, which is a non-diagonal matrix. So you make the product, the end-to-end channel, non-diagonal. So you could see this stacked version as a low complexity implementation of beyond diagonal race. Then, I mean, I will also go to kit research on fluid antennas, because you could make these antennas flexible. You could also optimize basically band basically. The reason why I'm telling you this is because W is not is fixed. It's not a variable of optimization. Once you fix the distance between the layers, this is done. But you could move the layers. Flexible antennas, or movable antennas, as basically like flexible antennas, I think. Okay. And so this is one of the other. This is one of the other things. Of course, I mean, it needs to be mentioned that from the performance point of view, these two devices, beyond diagonal and multi-layer, they are not the same because beyond diagonal, one single layer, so you don't attenuate the signals. Multi-layer, there is a lot of scattering between the layers. There could be the signal that comes back. So this needs to be, there are other problems, but at least you reduce the number of circuits and what the pros and cons are needs to be understood. I'm not saying that this is better than the others. I'm just saying that this could be viewed as a low complexity implementation. Okay? Who is the best? Which is the best? Not really clear. So, but I mean, I guess that the most exciting things for this theme, for me, is really to think of this device as a. I think that Carlo maybe will give a talk about this over-the-air computing. So it's really think something like that. So a device that you can put anywhere and it can do the computing, processing the signals directly in the electromagnetic domain. That's essentially the idea. And this again is not an idea that is, something that new in the sense that you will not find any papers on that, but people have been thinking in the field of metamaterials of doing really any kind of operations in the web domain. So you may take a signal and get it the derivative, the second order derivative, the integral. There is, for example, if you go to the papers published by another in GETA, you will find that he has built a device that does solve equations in the analog domain. Really solve equations. So of course, these people look at the fundamental proof of concept. There needs to be the first to do something. Maybe we need to do something else. I mean, more reconfigurable, or they can do many things with the same platform. But people are looking into that. So one example that we did, and then I will show you some results for each case study, is to optimize the system to do the DFT, the discrete Fourier transform. So this is just an example. The approach usually works for any kind of operations, but the DFT is useful if you want to do Isaac, or the direction of Ravel estimation, as I will tell you. So, but the concept is this. So imagine that you wanna compute the DFT of a signal. Essentially, what you need to do is to take the signal and multiply this signal by this matrix, and the output is essentially the. So, in principle, what you should do, you should now take the end-to-end response of this sigma, which is given, as I told you before, transmission coefficient multiplied by the propagation matrices, and your idea what it is to match F with G. Okay. Essentially, you could write an optimization problem, which is you minimize the error between F and G, And you do that by optimizing the transmission coefficient of the layers, because W are fixed once the. And in principle, you can do that for anything. So for any sort of operations that is known to a matrix, you could solve this optimization problem. If you go to the paper synoptics, they really take the machine learning approach. They say, I want to do something for which I don't have a mathematical expression. And so they use back propagation and all the kind of algorithms that people use. I mean, we are more like, model-aided machine learning guys, I guess. So that's the kind of things that we may interested in doing. I mean, here I take the occasion to tell you what is the structure of this upsilon, this transmission coefficient. As you can see, the usual RIS trick, transmission coefficient is equal to 1, the phase shift you can modify it. Of course, it's very ideal. Okay? What is going to happen with the signal that comes back when you are not able to transmit everything on that direction? That's a hard problem for the moment, but at least we get some upper bound here to see. So let me show you some results for these three examples. So here we consider the usual multi-user MIME problem, but the single version. So where we avoid the digital signal processing at the beginning and then we do the processing after. And we have multiple users. So the problem for the signal model that we consider between the layers is this one, which is, I mean, the simplest one that you can really use, the Rayleigh Sommerfeld diffraction model, completely scalar, so the easiest that we can consider, but at least we consider the near field effect. And also we consider this cosine, which is very important because I mean, otherwise the signal would explode if in some sense only a few unit cells contribute because of this cosine. So that's at least, I mean, is taken into account. By the way, this model, we did not propose it. In the paper synoptics, they utilized back in the days 2018 the same model. So we just utilized the same. And the problem formulation is the usual one for wireless people. So we maximize the sum rate. The SNR is defined in the usual way, in the sense that the interference is modeled as noise. And once again, we make the simplistic assumption that the transmission coefficient that are done one and the phase shift can be modified as you wish. Okay, so these are the results. On the vertical axis, the sum rate; on the horizontal axis, the number of RF chains. In blue, there is the zero forcing beamforming, and in red, what you can get with SIM. Here we have 7 layers because we have seen that 7 layers is the one that gives you the best performance. And then we have 2 case studies, one with 49 reconfigurable elements per layer, and another one with 100 reconfigurable elements per layer. We can see that at the end of the day, for the same number of RF chains here, you could, in principle, double the rate. Or you can see this in another way. In order to get, for example, this rate, zero forcing beamforming, will need 7 RF chains. On the other end, with SIM, you get fewer RF chains. So it's the same trade-off as a hybrid MIME. So in the sense, you play with these many reconfigurable elements, which are many more than the actual RF chains that you have, and you get basically a gain. So this is just to give you an idea of the gains that you get, but of course you save a lot in power. No, now the other question is what is the impact of these layers? So in principle, if I increase the number of layers, I get any gains, considering that we do not really have a non-linear benefit. So indeed, we did this study and we said that so let's take an area of that kind and we say, okay, we wanna create a beam pattern, a spatial beam pattern of that kind. It's a tool. So you can imagine that there you have a street, for example, and you want to make sure that the power is very high in that street and there is no leakage outside or whatever. So now what we did again, I mean, the problem can be solved as a sort of it's always an optimization problem. So what you want to do is this is your target. You want to reproduce, you want to optimize the SIM such that the output is this spatial power distribution. You have your target, so you have your power for every little block that you discretize your area, and then you want to optimize the scene such that the power at that point is as close as possible as your target. So the actual power, what it is? The actual power is the numerator of the SNR in this case, which depends on the end-to-end channel and which depends on the transmission coefficients. So you basically put everything in this optimization problem. You solve this optimization problem with the usual algorithms. There is not much innovation in the algorithms. And at the end of the day, you get that with simple with simple layers. Here, this is a binary metamaterials, binary metasurface for each layer. So only two phase shift for each metasurface. This is one layer. You are not really able to see to create that pattern because you don't have sufficient degrees of freedom for doing that. 3 layers start getting a little bit better. 5 layers you get a little slightly better, and then you get these 7 layers where things are really. You have a diminishing return low, but you can see there is this depth, effect. So the more the layers, the more the better your capability of beamforming beam steering. Okay. Of beam focusing. So now the most interesting things that I want to show you and is this direction of arrival. Yes, 5 minutes. Yeah. So there is this direction of arrival estimation. Here, I go fast so I can then show you the prototype. So the idea is the following. If we get a signal, and we don't know what the direction of arrival is, the signal goes through. We compute the DFT, and then at the output, we measure the received power at the point. What essentially we have here is that each point gives us the amount of power that is received from one specific direction. So let's take this element. This element would correspond to an angle of arrival from direction θ1. This here from direction θ2. This here from direction θ3. These 3 from direction θ4. So you have the distribution in power as a function of the angle. So at the end of the day, what you do, you measure the power of all these probes, and then you select the probe corresponding to the highest power. And from the probe that corresponds to the highest power, you can retrieve the angle. So in formulas, it looks like that. The signal goes through. You measure the power here, then you take the probe with the highest, the highest power. You get the index. From the index, you go back to the angle of arrival. That's essentially the algorithm, how it works. And it's interesting because you can do estimation without phase information, which is much simpler than the algorithms that are utilized. So, and this is just an example to show you what is going to happen if you compare a digital implementation figure B and a wave domain implementation, which is done through this scene. So, at the naked eye, you cannot really see the difference. There are minor differences if you zoom in, but it's pretty obvious. So now, at the end of the day, the concept is that we have noticed, even though there is no still a formal proof, except for saying that you have more variables, in principle things should go better, or maybe an informal proof might be if beyond diagonal reads is the optimal solution. We approximated beyond diagonal reads, and so we expect that the things improve, but there is not really a formal proof. But we managed to see that whether you do minor decoding, so communication-oriented performance metric, or you do a radar-oriented performance metric, it seems that increasing the number of layers gives you better performance. Okay, now a formal proof is still missing, but that's what we have. And now, very quickly, through some colleagues in China, actually, thanks to some two graduates from Central Sublec, one is my former PhD student, and another one worked with another colleague. Now they are back in China, and they read these papers, and they are in a department with all the hardware, etc. And they built this device. So they built multiple layers of transmitting metamaterials. Each metasurface is a binary metasurface, so each element can change 180 degrees the phase. And the testbed works at 5.8 gigahertz, so it's 1 bit, as I told you. and they made the test for 1 layer, 2 layers, and 3 layers. So the paper is published, is going to be published at Global. If you go to Global.com, I mean, we will present the paper there, or in any case, it's available on archive. But we considered 2 case studies. So the first case study is to enhance the received signal at the receiver when the signal goes through the same. And another is to estimate the direction of arrival of the transmitter when measuring the signal at the receiver when the signal goes through the same. And the results show that if the interlayer distance between the layers is less than lambda over 2, we notice that there is quite a good gains in terms of boosting the received power. So here, I mean, if you ask me, how did you optimize the SIM in this case? Brute force. In the sense that, because if you see at the paper is split into parts. One, we computed the grammar route bound and we do the optimization, nice. And then there is the experimental part where it's brute force. It means that we tried a number of code books, if you want, different configurations of the SIM. We tested all of them and we computed the solution that was giving us the best, just to see whether it was feasible. But I mean, going to the results, there are a few dB gain in communication performance, and also in reducing the estimation accuracy in terms of direction of arrival estimation. Now, what is going to happen if the interlayer is greater than lambda? The performance does not improve because we start having losses, etc. Now, even here we do miss a formal proof, but this is what the experiments show to us. Okay, so now I conclude. There is a few papers here. I mean, you can have a look if you're interested. There are many papers. There are more than 50, 60 papers so far, but that's what you will find. And so, if you're interested in knowing what is happening, the first paper we are about to submit it, and it gives you more the perspective from the optics, etc. The second one is a paper that I was asked to write. It's an embedded, convened session, EUCAP 2025. This is really state of the art. So what you will find is all the papers published so far in this area and split into different sections, and I make some comments, nothing more than that. But to the best of my knowledge, it includes all the papers available in the literature so far. So this could be helpful for a state of the art review. And then, I mean, one of the things that we are also quite excited about is kit research work, which is basically these flexible materials. Okay, so and indeed we call this, I mean, fluid here. I mean, we call it the name. So flexible intelligent metasurfaces. So the idea is that you take your substrate and the substrate can be bent. There are now prototypes that do that. This goes along the lines of it basically research work, and I mean, these are some examples of structure that can be bent. Of course, I mean, there are physical limitations on how much you can bend these things. But I mean, this will give you another degrees of freedom, because now this channel matrix is fixed. If you are able to bend the substrate, you will be able also to optimize this substrate. I stop here. I don't go much to the details. I don't have time. But if you are interested in the two references that talk about these flexible intelligent surfaces, this is a paper with NEC in Germany, where we use also an electromagnetic model, which is quite interesting. You can have a look. And this was accepted yesterday. It's flexible intelligent metasurface, done with the same group as of SIM in NTU Singapore. So this is more a conventional model, and this is a more practical model. Okay, that's essentially the idea. So I guess that I stop here. So again, thank you very much for